Welcome to the course unit titled Formal Languages and Automata. The course code is CPS 2005. My name is Adrian Francalanza, and I will be the person in charge of delivering this course. In this course, we will be talking essentially about languages. Most of you are already familiar with for example, English language. But there are other examples, such as the language of mathematics or the language of logic. Now, typically, a language can be decomposed into two parts. There is the syntax aspect and the semantics aspect. Syntax concerns itself with form or structure of the sentences belonging to that language, whereas semantics concerns itself with the meaning of those sentences. Let me give you a few examples. In the case of English, we could have the sentence, "Dogs like bones." Now, the sentence is of the right syntactic structure. Why? Because it has the form noun, verb, noun. It also means something, right? When we read this sentence, we can infer that dogs happen to like these objects called bones. The second sentence is also of the required syntactic form. In fact, we have a noun, ideas, we have a verb, think, and we have another verb, bones. So this is syntactically correct. However, the sentence is not semantically correct, because arguably it does not mean anything. The last sentence there, it is semantically incorrect, clearly, but also syntactically incorrect, because we have a verb, a noun, and a noun. And this is not of the correct form. Let's see other examples. In the case of mathematics, the first sentence is both syntactically and semantically correct. It is syntactically correct because we have an operator. We have a number, an operator, and a number, which is arguably of the required structure. It also means something. In fact, if I tell you what does that expression evaluate to, you would probably say the value 3. The second sentence is syntactically correct as well, because you have a number, an operator, and another number. However, semantically, it does not mean anything, because you cannot divide by 0. The last sentence is both semantically and syntactically incorrect, because in this case we have an operator, another operator, and then a number. And this is arguably not allowed in the language of mathematics. If we had to look at the last example, which is that of logic, the first sentence, P or Q, that is both semantically and syntactically correct. Okay? Once again, this is syntactically correct because we have a literal, an operator, and another literal. The second sentence, we could argue that it is also syntactically correct, But semantically, some could argue that it is incorrect, because you can never find a truth assignment for P that would make P and not P evaluated true. So this could argue that it is not part of our language. The last sentence, it is syntactically and semantically incorrect. It is clearly syntactically incorrect because here we have an operator, a unary operator, which is the negation. Then we have a binary operator, the and then we have P. In this course, the good news is that we will mainly be dealing with syntax. If you're interested in semantics, there are courses in the third year that you can take. So, more concretely, what is a language? A language is a set, and last year you have covered the notion of sets. It is a set of strings. The question that you should pose is, what is a string? You should have covered these last year as well. But let's go over it again. A string is just a sequence of alphabet symbols. The question that you may be posing is, again, what is an alphabet? An alphabet is just a set of basic building blocks. So to give you an analogy, think of Legos. So Legos, you have these basic building blocks. With these basic building blocks, you can build toy houses, right? This would be your sentence, right? Or your strings. And then your language would be all the toy houses that you can build using these basic building blocks. If you're still unsure about what I just said, I will give you another more concrete example. So, an example of an alphabet would be the set containing two basic building blocks, and I'm going to call them A and B. With these basic building blocks, you can construct the following strings. For example, you can construct the string that starts with an A, is followed by a B, is followed by another A, and then ends with another A. You could also have this string, which consists of a B followed by another B. Curiously and importantly, you could also have the empty string that contains no building blocks. This is a valid form of string. An example of a language based on this alphabet would be all the strings that you can build with these building blocks, right? In this fashion, in this fashion of strings, such that these strings, they all start with an A. So this would be an example of a language. All the strings starting with an A. There are other examples of languages. For example, I could define a language that contains all the strings that contain 3 B's. They can appear anywhere in the string, but every string in my language should contain at least 3 B's. These are examples of languages. Before I proceed, I would like to go over or brush up a bit of the basic concepts that we will be using in this course. Note that strings are different from sets in 2 important ways. The first important aspect of strings is that order is important. So, for example, the string starting with an A and then followed by a B is not the same as the string starting with a B and then followed by an A. In the case of sets, order does not matter. In the case of strings, repetition is also important. So, for example, if you have a string containing an A followed by another A, it is not the same thing as the string containing just that one A. This is not the case for sets. This may be revision to some of you, but I will just repeat. I will just go over a few operations on strings. So strings have this constructor operator. What does a constructor operator do? A constructor operator takes an element of your alphabet, in this case A, it takes a string and it puts that element of that alphabet in front of that string, returning this string, in this case A followed by B, followed by B, followed by A. This is another example of using the constructor or cons operator. You can take A, which is one of the basic building blocks of your alphabet, right? And you can also construct it or cons it with the empty string. This would give you the string containing A. Another operation on strings is the catenation, that takes a string and another string and returns back the catenation of those two strings. So for example, you could take the string containing A followed by a B and you can catenate it with the empty string. And this would give you what? It would give you back the string containing A and B. Similarly, if you take the empty string and you catenate it with the string containing A followed by a B and then followed by another B, you would get back again that same string. Throughout this course, we will be using strings all the time. So we will develop a more lightweight notation to represent strings. In particular, we will be dropping the square brackets and we will be dropping the commas between the basic building blocks. And in the case of the string, we will just represent it as A, B, A, A. Similarly, if you want to write the string, you can just denote it as B followed by a B. Things get a bit tricky in the case of the empty string, because if you drop off the first square bracket and the end square bracket, right, you would end up with nothing. Because of this, we will use a special symbol called epsilon to denote the empty string. Typically, I will denote an alphabet using the Greek symbol sigma. If I want to represent all the strings that you can build with the basic building blocks defined in sigma, I will refer to this set. So this is the set of all the strings that you can build with the alphabet sigma. I will refer to this as sigma star. For example, if my sigma is the set containing the alphabet A, B, and C, I can build the following strings. I can build epsilon, of course. I can build just the string containing A. I can build also the string containing A followed by a C, or the string containing a B followed by a B. I could also build the string A followed by a B followed by another A, so on and so forth. Notice that sometimes it is hard to distinguish between the string containing just A and the alphabet A. Usually, the context will allow us to disambiguate between the two. But whenever this is not clear, feel free to disambiguate yourself by making this distinction explicit. Most of you are already familiar with the notion of a variable. So for example, when in mathematics you write x plus 1, you know that x denotes some integer value. You don't really care what it actually is precisely, but you know that there is some integer x. We'll use the same concept here. So typically, I will refer to alphabet symbols using the variable alpha or beta. If I want to refer, right, to a string, but I don't care about the specifics of that string, right? If I want to use a variable to range over strings, I will use the variables s and t. And if I want to refer to a language via a variable, I will typically use the variables L, capital L, and capital K. Notice that a string is an element of sigma star, whereas a language is a subset of sigma star. I will also sometimes use a shorthand notation to represent string catenation. So sometimes I will write the variable s followed by t to denote the string s catenated with the string t. Similarly, I will also have a shorthand notation for the cons operator, and if I write alpha followed by s, that denotes alpha, which is const to the string s. Let me give you a few examples. What do you think this notation denotes? Well, that denotes any string that starts with the specific alphabet letter A. What does this notation denote? Well, it denotes any string, right, that starts with 3 consecutive B's. What about the last example here? Well, this denotes any string that contains 2 consecutive A's somewhere in the middle. So you could have anything in front, possibly nothing, possibly epsilon. You can have anything at the back, right? But somewhere in the middle, you should have 2 consecutive A's. In this course, we will concern ourselves mainly with this fundamental question. Is a string part of any specific language? It seems like a very simple question, but it has a profound connection to computer science. For instance, this is the fundamental question underlying any compiler. So every time you write a piece of code, right, your program would be typically represented as a string. Your language, right, Java, C, Python, or whatever is fancy nowadays, right, would be your language, right? And when you compile it, right, what you're doing there is you're trying to determine whether that program belongs to that language, is a valid element of that language. Now, there are a number of questions that you may ask, or that you may derive from this simple question. For example, how can I describe this language? Right? Can I describe this language precisely and finitely? How easy is it to determine whether a particular string belongs to that language? Are there different formats that would allow me to determine whether a string is in a language more easily than other formats? So on and so forth. So, if you are interested in things like this, you should be enjoying this course. See you next time.